Hi, I am Professor Shiva panchakshari. In this video, I'm going to explain about the concept of curl. So in this video, we understand the meaning of three words specifically: circulation, circulation density, and then we go for curl. Circulation and circulation density are very much required to understand the concept of curl. Okay. Let us see what is circulation first. Let us take an example, a real-time example. Consider a river in which water is flowing with the different velocities at the different heights. Let us assume that the velocity of the water is maximum at the surface and minimum at the water bed. So if you come across an object, something like a stick or some paper or maybe a pedaling wheel in the water, then the wheel or the stick or any object experiences a force due to this velocity gradient. Whenever there is a change in velocity, then we can say that there is a gradient of velocity. Due to this velocity gradient, the different parts of this object experience different values of force. Let us say the top part of the object experience more force due to larger velocity than the force is acting in this direction. At the same time, the lower part of the object experiences less force compared to the force on the top surface, and this value will be very less compared to the top force component, due to which the object experiences a rotational force or a circulation force, and it starts rotating in this direction, that is clockwise. In the second figure, we can see exactly opposite kind of situation where the lower part experiences highest force, maximum force in this direction, that is counterclockwise, and top surface less force, due to which the resultant force acting on the wheel will be in the counterclockwise direction. This kind of forces are called circulation force. And if you take a look at that third example here, the object is not experiencing a velocity gradient here. The velocity acting on the object is same. That's why this object doesn't experience any circulation force, and the force acting is linear. The object moves in the direction of the flow. That means whenever this kind of situation occurs, we can see circulation of force. We can call them circulation of some force induced by the velocity gradient. And in mathematics, we express the circulations as integral of the force over closed path. Integral of the force over closed path. So for that, we shall go for more examples. Let us take few more situations here. See the figure number 1, in which I have taken a rectangular object placed in a vector field, let us say F. F is having direction towards the right, from left to the right, and the rectangular object is placed in that one. And I have chosen the direction for the closed path also. So the closed path C is taken in the counterclockwise direction. If you analyze the component of the force, if you find the component of the force acting on each side of the rectangular object, then we may get some idea about the circulation. Let us take the component of the force acting on the first side. Take this side, the first side of the rectangle. See, the direction of the side and the direction of the force both are in the same direction. So that means, so we can assume that the rectangular side, number 1, is experiencing force in this direction, and they are parallel to each other. The angle between them is 0 degree. So most part of the object is experiencing the force. Since they are in the same direction, the component of the force on this one will be positive, let us say. And if you come to the second side of the rectangle, here they are perpendicular to each other. The amount of area of this side to come acrossing this force is very less. So the amount of force acting on the side number 2 is also negligible. So after seeing this concept, so we can say that if the angle between the path or the side and the force is 0 degree, it experiences more force, and 90 degree doesn't experience much force. So we can put this concept as a dot product, which will take care of the direction. So F dot dl is given by F dl cos theta. If theta is 0 degree, where theta is the angle between the force and the path chosen, if theta is 0 degree, cos 0 becomes 1, the maximum force is experienced, F into dl. If theta is 90 degree, as in the case of side 2, then cos 90 becomes 0, no force is experienced. So if you continue analyzing in the same way, if you come to the top, the part of the rectangle, that is side number 3, then the angle between these two is 180 degree, are opposite to each other, but still parallel. So we can say that the force is negative here. If you introduce 180 degree for cos theta, you can find the negative force on this one. But this force is equal to the force acting on the side number 1, but opposite in polarity. And if you go to side number 4, angle is 90 degree, no force is acting. So if you add all the 4 components of this force here, we can say that force on the first. So let us go for addition. So which can be implemented using the integration over the closed path. And on the first one, it is FDL. Second one, it is 0. And the third one, it is minus FDL. Then on the fourth one is again 0. And if you add all of them, it's going to be 0. That means no circulation happens on this rectangular closed path because the force is introducing same kind of force on the side number 3 and side number 4. Both are pushed in the same direction. So there is no scope for revolution about its axis. So that's why we can say that no circulation of the object after the object takes place. If at all, if it is there, it is only a linear force acting in the direction of the force itself. If you look into the figure number 2, there force acting on side number 1 is as usual positive. Number 2, it is 0. And number 3, it is in the opposite direction. Again, the angle between these two is 0 here. And this is also positive here. And this side it is 0. So the point to be noted in this case, the force and the path are parallel. Here also force and the path are parallel. So both are going to be positive. So as in the first case, they are not getting cancelled here. They are getting added up. So that's why the total circulation, if you find in the figure number 2, is going to be 2 times FDL. So that's why this rectangular object experiences a rotational force or a circulation of the force, and it starts revolving. You can easily predict the direction of revolution. So that is, this side rotates in this direction and this edge in this direction, so that you can see some rotational force on the rectangular object. So now we can say that there is a circulation of force, and mathematically it can be written as closed path integral of the force F about the path. In the third, here, the side number 1 positive, side number 2 0, side number 3 also positive over this one, but here some part you can see here. So sorry, this is negative and this is a little bit positive. So compared to this first one, so there is some component which is producing circulation here. Here on the side one, we are finding more force. And the side 3, we are seeing very less force pushing in the counterclockwise direction. So rest of the things will be getting cancelled. So that's why in the figure number 3 also there is a small circulation, but not as much as that of figure number 2. And if you go to the figure number 4, the last one, here you can see the different sides of the rectangle experience different kinds of force components. They are randomly distributed. So that's why we can say there is also some circulation. So which can be obtained through the integration of the force with the path component. So with these examples, we can see that one by adding all the force components, we can find the total circulation here. And the last condition, that is the fourth condition, we can see that the circulation acting on different points within the closed path are different. See their direction of force. If you choose rectangle, smaller rectangular closed paths within that bigger rectangle, we can calculate the circulation separately and we can add all of them. So what I mean is, if you want the total circulation produced over the closed rectangular path under consideration, that is called C, which can be obtained by summing the circulations of force F and the smaller closed paths within them, and we can take them as summation like this. So the total circulation can be taken as sum of all the circulations of this. So for more information on this concept, let me take one more situation. Here I've chosen a small circular path C1 and an adjacent another circular path C2. Both of them are having some area, same area, let us say delta S. Then the circulation directions, if you see the arrow mark I have taken, it is acting in counterclockwise direction and they are side by side. And if you see this part here, they are adjacent to each other. If they are meeting each other, if they are sharing the same side, then you can see the arrow marks. That is, the force components are in the opposite direction. They get cancelled out. So the overall circulation of these two small circular paths can be summarized as the outermost circular path. That means the common branches or common sides shared by the neighboring areas or circulations can be neglected or cancelled. So that means the total circulation of force acting on any closed path or clears the object or on the extreme surface will be simply evaluated on the outermost boundary of the object. So we need not to analyze for every small circulations. So what we can say that is the sum of all the circulations over smaller closed path within a large most closed path is simply given by this mathematical relation. So that means it is required to find the total circulation only through boundary. We need not to analyze for every smaller surface. So the overall circulation is F dot dl. And if you see, compare all these examples here, the area also matters. So larger area include more circulations, lesser area includes less circulations. So to analyze, to quantify, to find the magnitude or amount of circulations experienced by any closed path, so we need to introduce the area enclosed by the circulation path into the mathematics. So we introduce the word called circulation density at this point of time. So that the circulation density is the number of circulations per unit area. So we have to introduce area into the denominator to get the concept of circulation density. So that what does it mean here? If you take a closed path C, let us say, then the closed path C may be having smaller circulations within it. Some may be acting in clockwise direction and some may be in counterclockwise direction, like this. So the number of circulations enclosed by this path divided by area will give the concept of circulation density. So finally, circulation density is the circulations per unit area. Now it's the right time to introduce the word curl. The curl of vector, say F, is given by circulation of the force F per unit area. The area I've taken to be a small value as the area tends to 0. Let us look into physical meaning of this equation here. The circulation of F over a closed path. So in the previous diagram, the circulation of F over this closed path divided by this area. The area has to be very small. Hence, limit is introduced here. The area should tend to 0. That means the area should shrink to 0. When the closed path C shrinks to 0, so this becomes a very small closed path. All the closed paths, when they shrink to a smaller value, they become almost equal to circular paths revolving around a path. Now the area shrinks to very smaller value, then it can be treated as a path. So this delta S area now can be addressed as a point. So that means the circulation of force around delta S becomes circulation of F around a point, otherwise circulation at a point. Since circulation is taken per unit area, we can call it circulation density of vector F at a point. That means limit introduce the concept of point here. Then at a point is called curl F. That means curl of a vector is simply the circulation density of the vector at a point. So physically, curl of any vector is circulation density or circulation per unit area of the vector F at a point. That means the word curl cannot be used when we try to explain the revolution of an object of larger area or a larger closed path. So curl is defined only for a particular point. So if you want to define the circulation of a closed path, it has to be explained at a particular point. So that is it. So curl is the operation which introduces revolution or revolve or rotational force to a particular object about its own axis. Let me give you some physical examples in which this concept of curl is used. For example, first one, if you consider electric field E, which is a vector produced by a static charge distribution. We know that electric charges produce electric field if the charge is static, not varying with respect to time. That time, electric field produced by the static charge distribution is diverging in nature. That means if you consider positive charge, the electric field diverges in all the directions. And the stream lines of electric field, that means flux lines of electric field are straight lines. The move away from the positive charge, they go towards infinity and terminate at infinity. So these lines of electric field are not rotational in nature, they are irrotational. So we used to explain the concept of electric field of static charges. Del cross E is equal to 0. This mathematical equation will be learned later. So time being, it's called curl E is equal to 0. It means that electric field is not rotational. Curl of electric field is always 0. It happens in negative charge also. For negative charge, electric field converges at the negative charge, and the curl of electric field is always equal to 0. On the contrary, if you take the magnetic field produced, the magnetic field H produced by a current I flowing through a conductor. If you consider a current carrying conductor or a wire, then the magnetic field is produced around the wire is rotational. That means curl of magnetic field is possible, and it is given by current density, nothing but current by area. So what does it mean? It means that if you choose a current carrying conductor, say I, then if you want to measure magnetic field at a point here, say H, and this magnetic field is rotational at that point. So can also find the magnetic field in many applications revolving around this current carrying conductor. So we can say that the total magnetic field around this closed path is given by circulation of magnetic field about this closed path. Let us say C is equal to the total current within this closed path. And this is the Ampere's law, which says that the magnetic field is rotational and it is revolving around the current carrying conductor, and its magnitude is given by the closed path integration of H, which is equal to the total current value. If you want to know the magnetic field at a particular point on this path, not on the complete path, at a point, then it is curl H is equal to J. J is not the current, it is the current density, because curl includes circulation density. So circulation density of H at a point is equal to current density at that point, or simply curl H is equal to current density at that point. So these kind of applications are come across in subjects like fluid mechanics, electromagnetics, and many other subjects where curl is playing a vital role in understanding concepts. That's about for this video. Thank you, guys.